This webinar is related to how to select the academic projects. This is all my experience when I used to guide students. Since 2006 I am into a training business of CFD. So I have realized that students do a lot of mistakes, during selection of the project, during execution of the project. They being in academics, they do not have a true required professional approach towards CFD. So what I thought of is I thought of coming up with some rules which will guide them while selecting the project. So this is the intention of this whole presentation, just to make sure that we do not go in a wrong path. The intention is not to discourage anyone from selecting complex project, because few of the rules which I have written, they are like the sound is like don't go for a complex project or something, but the intention is not like discourage anyone to select complex project. The intention is also not to say that it is too late now and it is impossible to do CFD project. Intention is not that. Intention is that you start early, plan well, and then the project would go very smooth. So the intention is to share what should be done, or what is the best way to select and do a good CFD project. And the intention is also to share some guidelines to avoid unfinished project work, because I have seen many people starting with very good project ideas, but at the end of their academic year they end up into doing something very small, or maybe they'll end up into unfinished project. So intention is to share some guidelines to avoid that situation. This is the overall agenda. I have written something like 10 rules about what should be done when you select academic projects. We will try to review those rules, and we will also see CFD Complexity Matrix, in the sense which problem is simple, which problem is complex, something like that. We will also see CFD learning curve. If you are a beginner in CFD, what is the typical learning curve, and how much time is necessary to learn particular skill sets. So we will also discuss that at the end of the webinar. I will also share some problem definitions, sample projects which are designed considering all these rules. So we will also share some sample projects. And then what are the different ways by which you can get connected to us. So I'll share some details about it, and at the end of the day, end of the webinar, we will have a question and answer session. Okay, so let's start with the rules. So the first rule is just don't forget the purpose of the project in the academics. Typically what happens is we go for very complex definitions, and we forget why there is a project work in the academics. So it is not just a project done, credit acquired, and it's not just a part of a curriculum. It's a very important stage as far as academics is concerned. The main purpose of being project in the academics is we learn a lot of theory, we learn a lot of concepts. Now this is the time, the project is the time where you can apply that theory, apply that knowledge on some practical cases. So this is the main purpose, that you have acquired certain knowledge over the years during your academics, and the project work is there to apply that knowledge on some practical cases. So that is the main purpose of project being there in academics, and that too at the end of the academics. This is also very a good way of learning project execution process, because once we finish the academics and go in the industry, they have their own processes, they have to go through certain stages when it comes to every project. So we need to make sure that we have through the academic project we learn the project execution process. The next way is, this is the most critical part as far as your way to the industrial jobs are concerned, because most of the cases I have seen that industrial jobs, the opportunities, the career is decided based on what academic project is done. So It is one way, it is very important way to get into the industrial job. So just not forget what is the purpose of the project in the academics, and make sure that we satisfy all the necessary requirements. I have seen this, that is why the second rule says that gold is awesome but it's metal, we cannot eat it, we are hungry, we want to satisfy our hunger. Although gold looks good but we cannot eat. It means that although CFD project looks very catchy in terms of their further career opportunities or the execution process itself, it looks really good, but the academic project work has to be selected based on the career goal. It means if I want to make a career in CFD, then only I should select CFD project. We have to visualize when we are in academics, at the end of the academics, that what are my career goals, what are the typical jobs that I would like to do, I would love to do, what are the typical companies in which I would like to do the job, and what is the typical profile I am looking for, wherein I will be happy doing that job for years. So everyone in the academics has to define their career goals, has to define their dream job, and based on that only we need to select the project. Although it may not be CFD, it may be CFD, but the CFD project selection should be based on all these criteria. The second important thing that we need to do, or every student has to do, is visualize what's it going to be. When you start working as a CFD engineer on daily basis, so if you like that job, talk to few people who are working in the industry in the similar domain, ask them what are the jobs that they are doing, and if you feel that those are the jobs that you would love to do, then it makes a lot of sense to go for CFD as your project. So select the project based on the career goals. Do not select the project based on the market trends. We have to think about what is there in the market, but that should not be the only criteria. That should not be the only basis for selecting the project. Definitely do not select projects based on what your seniors has done, because what they have done might not be of your interest. So the theme line of this particular rule is decide what is your career goal, decide what job that you would like to do, and if you feel that okay, CFD engineer is the profile I am looking for, then go for CFD. So make sure that you select the project based on these goals or based on this rule. Understand the importance of the project in the academics. Project can make or break career. I have seen people with excellent academics but not very good project, and personally I have rejected them for few of the openings that we have. I have seen people with bad academics but excellent project work, and they go far in terms of the career opportunities. So project work is the one which can make or break anyone's career. This is one way to dig your path to the industry, because the moment you go in industry, they would start asking you they would deploy you on some real projects. So academic project is the one by which you can prove that okay, I am capable of handling the real case, I am capable of handling the industrial project. So that is one way to dig your path to the industry. Has a potential to overcome any limitations in the academics. I have seen people with bad academics, I have seen people with a year drop in their academics or something like that, but I have seen those people doing excellent project work, and all those limitations would go away. So it has a potential, project work has a potential to overcome any limitation in the academics. And this is definitely the most important aspect for industry. The first thing that we check is what is the project work somebody has done, and if that falls into the job profile we are looking at, so we definitely give a higher preference for them. This is not only related to us, any industry we talk about also follows the similar kind of rule. So project work, to summarize, is a very important part as far as your academics is concerned. Know what you know and what you don't. This is one limitation I have seen as far as CFD is concerned, that people select the project but they do not understand that what is the knowledge that they currently have and what is the knowledge that they need to acquire. So based on all the above rules, rule 1 to 3, we have selected a good project. That is fine, everything is going good. But what about the tools, the knowledge required to execute the project? Do you have that knowledge? Do you have the knowledge of the tools or the software, or do you have a knowledge of fundamentals to execute that project? So that is also one thing that we need to consider while selecting the project. Understand what knowledge you have and what you need to acquire. Whenever you select a CFD project, you have to analyze yourself and see what are the subjects that you have gone through when you during your academics, what are the additional subjects that you have to go through, and what are the additional softwares that you have to learn to execute the project. So that is also we need to analyze when we select the project. This is also very important. Learning CFD needs time. So see if you have that time or not. It means I have seen people asking me that can we do a CFD project when the time remaining time in their academics is about 2 months or 3 months. So it becomes at that point it becomes almost impossible for them to acquire the knowledge and they execute project. So one thing we need to understand is whenever we go for CFD project, we need to learn something, and that learning is going to take some time. So we have to make sure that we have that time available with us. This is my own philosophy. Everyone can do everything, but everything needs time. I mean, nothing is impossible, but when you apply a time constraint, everything becomes impossible if there is no sufficient time for it. So definitely if you have enough time, you can do a lot of things in CFD. So make sure that we have that time, or make sure that we start early. Pardon my language in the rule, but this is true. Sooner the better, but later the sucker. So it literally creates a lot of problem when it comes to the time constraint. As I said, everything needs time, and unfortunately CFD needs more time, in the sense it is there are certain things which are a bit complex to understand. So it needs some time. It needs more time to understand it, grasp it, and then apply it for your project. So if you start early in CFD, you can go deeper, in the sense you can start with a simple problem and you can go more deep into, making that problem complex. So if you start early, you can go really deep into CFD. I have seen this, great ideas get converted into a normal idea or almost nothing idea only because of the time. I have seen students coming up with really great ideas for their CFD projects, but only because of the time constraint they do a lot of approximations, simplifications. So the great idea gets converted into something, or great project gets converted into something called as normal project, or almost nothing, only because of the time constraint. So start soon, start early, go slow, explore more, and enjoy the journey, because CFD, the moment you stop enjoying learning CFD, you will stop doing CFD. So it's always better to start early, go slow, and definitely enjoy the journey of learning CFD. This is one important aspect because that is one of the limitations when I talk to different engineering colleges, their professors or students, that it's very well understood that we need guidance. We cannot do something from scratch. We always need guidance. We always look for guidance from our colleagues, our friends, or our mentors, our guides. So everything needs the guidance, and in fact CFD needs a great guidance. If we do not have a good guide to guide the student, then it would become very difficult for them to conduct the project. So whenever we are going to select the project, make sure that what is the knowledge your guide has, or what are the different ways that you can opt for the guide or something like that. So guidance is very important. We need to know the strength of our guide, or I would say a guiding light. And there are other options also. If we do not have an in-house guide, or if you do not have a good guide or knowledgeable guide at your institute, There are other options that you can opt for a good guide, good mentor who would guide you through your project. So whenever you select a CFD project, make sure that you need guidance and also have some options available, do some literature survey and have some options available for getting the guidance either in-house in your institute or from some external sources. This is all related to the complexity. I say moon is far away. We can reach to the moon, but it's a far away. So we have to spend time about reaching there. So whenever we select a project, know your limitations about knowledge and time. What knowledge you have and how much time that you have. So have that idea in your mind and see how complex project that you are defining. Complex CFD project always sounds good and looks attractive at the initial stage. It's very good to do complex project, but do you have a sufficient time and the knowledge? Have you planned it correctly? So that is one aspect that we need to think of when we select the project. Do a good literature survey about time taken for similar projects, because sometimes what happens is we select the project and we really don't know how much time it is going to take for me to learn it, me to do the project. So one way that we can think of is do a literature survey, find out if somebody else has done a similar work or not, and see how much time that he has taken, in the sense was it his master's thesis, was it his bachelor's thesis, was it his PhD thesis. So based on that you can estimate that okay, that person has taken that much time, so probably I will also take similar amount of a time. So if I see a project done by a PhD student is selected by an MTech student, that would become almost impossible to achieve, because the PhD student generally spends about 3 to 4 years on his thesis, and MTech student gets about 6 months or a year maximum for doing the project. So do a good literature survey about time taken for similar projects. That would give you some guideline about the complexity and how much time probably you would also take. One thing that we can do, which I always suggest, is initially when you are defining a problem, start with easy one. Chop down, do some approximations at geometry or physics level. Start with easy problem and then you can increase the complexity of the problem. So that is the way we can go. So make sure that you have sufficient time, you have planned it correctly again to solve CFD problems. Sometimes simple becomes complex. Whenever I talk to students, they say that flow over a cylinder is a very simple problem to do, but it sounds good, simple, but it's not simple to do. The moment you start adding complexities into it, it becomes a complex problem. So it's very important to know what is the complexity of your CFD problem, and literature survey is the stage which becomes very critical to understand it, that what is the complexity of the project. So know what the complexity of your project is. I am going to give some guidelines about what is simple and what is complex at the end of this webinar. Typically, as far as CFD is concerned, we talk about two levels of complexities. One is either your problem has complex geometry. For example, we are talking about a vent design of a car, or we are talking about a turbo machinery design, or we are talking about a complex heat exchanger design. So that is a complex geometry. It's not simple geometry to handle. The second level of complexity is complex physics. For example, we are talking about a phase change, we are talking about interaction of multiple species. So that is a complex physics. So there are two levels of complexities whenever CFD project is concerned. One is the geometry level complexity and other is a physics level complexity. Generally what I suggest is try to have one of them. Either select a complex geometry and simple physics, or select a simple physics and or simple geometry and complex physics. Do not start with both of them, because if you start with both of them, you have to have that much time to handle that complexity. So although sometimes simple looks simple, but it's not simple, it's complex in terms of CFD. So make sure that you have understood the complexity of your project very well. I have seen this also, that most of the students end their project just at, by doing the project presentation in front of their professors. So I think that is not the case. We have done good work, right? I mean, we have done good project work, So it is not just about telling your professor what you have done, or once the presentation is done your project is done. It's not something like that. We need to do is we need to broadcast that, we need to get it reviewed by people outside. That is the only way by which you can get the feedback about your work. That is the only way by which you can get the appreciation for your work. So just not finish your project by doing your final project presentation in the institute. So we need to get a feedback from the experts. We need to get it broadcasted. That is the only way by which you can extract the maximum benefits from it. You have spent about 6 months or a year on your project, so it's time for you to extract maximum benefits. So the way you can do it is by broadcasting your work, publish a paper, present it at a conference, talk to people and get their feedback, see how what they feel about your project and all. So just not finish your project by doing a final project presentation in the institute. Think about publishing a paper, think about presenting it at the conference, and this you have to plan way early in your project stage. For example, let's say you have a year in hand, so you have to think about, okay, in 8 months I am going to finish my project with a final project report, and remaining 2 months I am going to write a paper, I am going to search for a conference, and I am going to present my work there. So you have to plan it accordingly, so that you get enough time to do all these activities. So the rule says that plant the seeds, grow them, and harvest the crop. Extract the maximum possible benefits from the project. This is a very critical rule, that you cannot dig a well with fork. It means you have to have a sufficient tool available with you to do a particular job. So what I have seen is people do a literature survey while selecting their project. They do a literature survey, find out some problem definition over the internet, but they forget about one aspect is who has done that project. Most of the time I have seen people coming to me with a paper which is actually presented by some PhD guy, and the person coming is actually MTech or bachelors student. So the important stage when you do a literature survey is to identify what are the different problems that people are solving, and also to identify who have done those problems, how much time they have spent. One more part that I see is, if you are going to do CFD project, you have to think about, are you going to use a standard commercial softwares like ANSYS Fluent, CFX or CCM Plus, or any other software available. So I have seen few of the project which needs some tweaking, which needs some customization for that software. I have seen some projects in which they do write their own programs, they do write their own codes for doing a CFD simulation. So if we are thinking that I am going to do a similar work using these commercial softwares, we have to think about how exactly we are going to do it. Are we going to write some customized codes and hook into our softwares, or are we going to use the standard functionalities available in the software? So we have to have a right tools available in hand to make sure that we do that project correctly. So whenever we select a project, make sure that how that project is done, what softwares that they have used, what models that they have used, and make sure that you are going to learn it and then you are going to use it. So customized code is almost writing a customized code or writing your own algorithm discretization method takes time. So make sure that you are aware of it. Find what CFD tools, as I said, find what CFD tools, CFD codes are used in the similar work, so that you can also think of using the same thing. See if you have a time, knowledge and access to those tools. Unless and until you have access to those tools, you cannot think of using those tools in your CFD project. So these were few of the guidelines, few of the rules as far as selection of the CFD project is concerned. These guidelines would help you to see what is the complexity of the project, how much time that you have, and plan correctly. Now let's talk more about the complexity matrix, in the sense, what is complex, what is simple. So I have used a famous contour plot, we call it as a contour plot, wherein bottom figure is bottom color is the low value, it represents the low value, and the top color, which is red, represents the high value. So whenever it comes to the geometry complexity, the domain size, domain definition complexity, 2D geometries are simple to handle, in the sense we can do a repairing, we can do meshing of 2D geometries very easily. 3D falls into a most complex category. 3D geometries are complex to handle. So in terms of geometry complexity, 2D is simple to handle, 3D is complex to handle. In terms of meshing complexity, meshing is the stage which we need to use to discretize our geometry. So there are different ways by which we can do it. One is unstructured tetrahedral mesh, another is unstructured tetrahedral plus prism mesh, then third is a multi-block hexahedral mesh. So the complexity of creating all tetrahedral mesh falls into lowest category. It is simple to create unstructured mesh even for complex geometries. When we go for tetra and prism, it is on a higher side because we need to create proper prism layers, we need to turn the prism layers correctly, so and so forth. So creating tetra and prism mesh is a bit complex as compared to creating only tetra meshing. Creating hybrid mesh is more complex than the tetra plus prism meshing. Hybrid mesh is one part you mesh it with hexa and another part you mesh it with tetra prism or tetra, so that is a hybrid mesh. The most complex type of mesh generation, I am referring to a complex geometries, I am not referring to a simple geometries. So the most complex is creating all hexahedral mesh using multi-block methodology. So that is the most complex meshing method as far as complex geometries are concerned, because it takes a lot of time to create a block structure, to map it correctly, and create a all hexa mesh. So whenever we think of doing a project, see what type of mesh that you are going to use. Probably you are going to do a literature survey and find out what typical mesh people will use, so probably you will also try to create that. Make sure that you understand the complexity. If you see that okay, I'm going to only use tetra meshing, you understand what is the complexity, how much learning is necessary for it. So this is complexity of domain and complexity of meshing. When it comes to the solution or solver side of complexity, or I would say physics side of complexity, solving laminar problems are simpler one. They are most simple problems in terms of complexity matrix. Then comes the turbulent. Solving turbulent problems are a bit complex. It takes some time to understand what turbulence model that we need to use and all other aspects of turbulence. So solving turbulent problems are a bit complex. Now when it comes to heat transfer, solving heat transfer with conduction and force convections are simpler. But solving problems with natural convection, they are a bit complex. They go into a complex category, all because of the convergence issues, because of the natural convection model that you are going to use. And when it comes to the radiation modeling, it is the highest complexity level in terms of when it comes to modeling heat transfer problems. So the problem which involves radiation is going to take more time, not in terms of the simulation time or the machine time or the computer time, but in terms of understanding how to model it and implementing it on your project. Now when it comes to a compressible flow, that is much more complex than the previous categories, because compressible flow, probably if it is supersonic flows, those things would come into picture. So converging compressible problems is a bit more complex, as well as learning the models which would do a compressible flow problems would be more complex also. Then comes the particulate flow. What do you mean by particulate flow is you have one phase, let's say air, and in air you have dust particles which are coming in and they are interacting with the air. So modeling particulate flow without reaction, but they do not have any reaction, so that is one problem. So that is in terms of multi-phase, it is lowest complexity. Then multi-species, in the sense, you have two gases coming in, but they are not reacting with each other. So you just want to know the mixing of those two gases. So that is higher level complexity. Then we have multi-species and particulate flow with reaction. Now they are reacting with the primary phase. Two species are coming together and they are reacting with each other and forming some product. Or maybe a particle is coming in, let's say water droplet is coming in and it is getting evaporated. So that I am calling it as a particulate flow with reaction. So that is higher complexity. The most complex problems to solve is phase change. I have a liquid coming in getting vaporized. I have a liquid coming in getting solidified, something like that. So phase change problems are a bit complex to solve. I mean, they are the most complex problems to solve. We would also have a similar categories about unsteady state problem and steady state problem, but I am not discussing that here. So the idea, or to my intention of sharing this complexity matrix with you is, whenever you select a project, make sure that what type of physics that you want to model and see where it falls. Is it a simple to do? Is it a complex thing to do? And if you are selecting something complex, you make sure that you have sufficient time to learn it and to implement it on the project. Now, as far as learning curve is concerned, I have just created a sample matrix. This is my own understanding of how much time it should take. It might take more or less time depending on the grasping capacity of the learner. So when it comes to meshing, I am referring to probably a tool which is ANSYS ICM CFD, which is a pre-processing tool. So when you start learning the software, probably geometry operations would take about a week for you to grasp it and learn it and apply it on some real geometry. So it would take about a week's time to do that. When it comes to a tetra meshing, it would take about 2 weeks time to learn tetra meshing. I am imagining something like 1 or 2 hours a day that you are spending learning these tools. So it should take about 2 weeks for you to understand how it works and create some mesh on some moderately complex geometry, not very high complexity level in terms of geometry. So it should take about 2 weeks of a time. Whenever it comes to a tetra plus prism meshing, it would take about 4 weeks of a time for you from day one to learn that technique. And multi-block hexa meshing, it would take about 8 weeks of a time to learn it. As far as multi-block hexa is concerned, I am considering low level complexity of geometry, because multi-block hexa needs a lot of time to practice. It's not only learning, it's also about practicing the technique, which would make you comfortable visualizing the blocking structure and all. So in general, it should take about 8 weeks for you to start doing some multi-blocking for some low level complex geometries. So this is a typical learning curve as far as meshing is concerned. So whenever you plan your project, make sure that you have at least 8 weeks in hand to learn meshing software, to learn a pre-processing software. When it comes to the solver, softwares like Fluent, CFX or CCM Plus, they are huge, in terms of their modeling capabilities. They can do almost everything that we can think of. To start with, we need not to learn everything, we need to learn things which are necessary for executing the project. So based on the complexity level of your project, you can think of, you can typically refer to this matrix and see how much time it would take. Again, the condition is about 2 hours a day. So laminar flows, you can start modeling laminar flows in about 2 weeks. So in 2 weeks you would be comfortable modeling them. Turbulent flows, it would take about 4 weeks to study something about turbulence models and see which one is applicable where and something like that. You will not be master into modeling turbulence or using turbulence model, but you will be comfortable at least selecting which one goes for my project. Conduction and force convection should take about 5 weeks. Natural convection should take about 6 weeks, and radiation should take about 8 weeks. So it means that if you spend about 8 weeks of a time, you can think of modeling heat transfer problem with turbulent conditions, or which falls into a turbulent zone. So if you have to typically spend about 8 weeks of a time to do that, to learn it. Compressible flows would take about 2 more weeks, about 10 weeks. Particulate flows without reaction would be approximately 11 weeks. When it comes to multi-species flow without reaction, it should take about 13 weeks. With reaction about 15 weeks, and with phase change about 18 weeks. It means if you spend 18 weeks of a time, 2 hours a day, you should be okay in handling some phase change problems. I'm not talking about very complex problems, but you can understand the terminology, you can start playing with the model, you can start playing with the software, you can start getting some results and start interpreting those results and ask questions whether they are correct, whether they are wrong or not. You can start, you will be a bit comfortable using the software. So it's about 18 weeks for physics, and it's I think about 8 weeks for meshing. So you should make sure that you have that much time available with you for learning all these tools. So this is the complexity matrix and learning curve for CFD. So based on all these criteria, we also have one program called as a mentor program, through which we offer a lot of projects to students. So based on all these criteria, we have defined some CFD projects. Currently we have defined projects only for master students. So this is one of the project. This is related to a turbomachinery. So we are not talking about a complex physics here, because the geometry is complex in this case. We are talking about a simple incompressible flow physics. But on top of that, what we are thinking of is, the whole project is oriented towards learning. If person does this project, he becomes more comfortable modeling turbomachinery. So it is like benchmarking the CFD methodology. It means using different turbulence model, using different boundary conditions, using different multiple reference frame models, and looking at what are the difference between the results and interpreting them, and finding out the best possible method to do a CFD simulation of a centrifugal pump. Another project is automation. Nowadays this is many people are talking about doing automation for CFD project. So this particular project is again a simple flow physics, probably simple geometry also, because it's a 2D airfoil. Flow physics is also simple. It's a turbulent flow without heat transfer. So flow physics is also simple. But in this project, what although as both geometry and physics is simple, we are thinking about automating the process. So that involves scripting. That involves scripting, automation for ICM, CFD, and Fluent. So this is the project. Simple physics, but needs some kind of a programming knowledge and scripting knowledge, some kind of thought process about integrating two softwares together, something like that. This is again one more project. So I'm just showing a sample projects, so you can imagine, everybody can imagine that these are the projects which are typically a very good problem definition as far as master's project is concerned. So you make sure that if you are thinking that these projects are simple, it means you have to lower down your expectations about your CFD project. If you are thinking that these projects are complex, you have to make sure that you upgrade your expectations, because if you select something simpler than this, that might not be a worth spending a year of time as far as master's thesis is concerned. So this is the project which is jet impingement cooling. So it involves heat transfer, and it is a 3D model, or it's a 3D problem. Okay, so there are other projects also which you can see. These are the links, learncx.com/mentor program. That is the main page wherein you can get more details about what is the philosophy of it, how it works. And if you would like to see the industrial projects are the one which we have. LearnCX does a lot of collaboration with industries, and that industry actually shares some problem definitions with us, which we offer to students. So you can see such kind of industrial projects. Currently they are the category or complexity of the project is for master level projects. We are also doing a background work to add bachelor level projects and even PhD level projects. So you can have a look at the list of the projects available there. Okay, I think that's all as far as presentation is concerned. You can always get connected with us. The website address is learncx.com. You can see the list of the courses as well as list of the industrial projects we are offering. We also have a huge knowledge base, like different webinars, recordings. We have a lot of blogs on CFD, so you can go on the website and start reading some stuff related to CFD. You can also get connected with us on different social medias, because we do a lot of knowledge sharing on the social medias. Also, we have very good groups on Google Plus and Facebook, which are like CFD Q&A group, CFD articles, news group, something like that. So go and get connected with us on social media also. So that's all from my side. If you have any questions after the webinar, you can contact me on this email ID. They are directed to me. So and I'll be very glad to answer any of your question. Thank you.